In this chapter, we will more focus on the practical most behavior model and behavior. This is the outline of this chapter, so we will learn review and transitional transistor IV curve. From that, we will explain the non-ideal transistor behavior, such as velocity saturation, channel length modulation, body effect, leakage, and temperature sensitivities. You have to know those effects, and also process and environmental variation, such as the process corners. Depending on corners, the VTH will vary, so we have to take that into account when you design your circuit. So first, we had learned that the Shockley first order transistor model like this. The cutoff for VGS less than threshold, it is zero current, and for VDS less than VD set, here VD set we define by the VGS minus VT in here, less than that, and the current will be governed by that linear equation. And if the VDS is larger than VDS, larger than VD set, VDS larger than VD set, then it will be saturation. Definitely for this condition, we are assuming that VGS greater than VT, right? So let's assume we have a 180 nanometer TSMC process. If we extract the value from this process, the beta is approximately like this, and VTH around 0.4 volt, and VDD is 1.8 volt. Using that information, if you just draw the I and VDS, IDS versus VDS curve, so we plug down those parameters into ideal scale law model, right? Beta VGS minus VT scale, right? For saturation, we have the equation for triode. So all these level behave like follows the ideal, the scale law model. But in reality, it isn't just that simple. So if you simulate the 180 nanometer process using the real spice, and you will see a little different curve, IDS versus VDS. What would be differ? We will see the next slide. So first, less on current. The current in the previous case, compared to ideal scale law model, the current level is smaller, so less current flow actually, and also it doesn't follow the scale law model because it has the level, so point here to there. If we let's pour VT equal 0.4 volt, the overdrive voltage in this case is 0.2, and here how much? 0.5. So VGS overdrive voltage is more than double from here, right? So current increased a little higher. For the other case, like from in this case to for here, for example, overdrive voltage for VGS equal 0.9 is 0.5, and for 1.2 VGS, so overdrive voltage is around 1.2 minus VTH, that is 0.4, that is 0.8 volt. So approximately how many? Approximately almost 2x larger overdrive voltage, but actual current it flows it's around 2x larger. It just doesn't follow the scale law model. If that would be scale law model, then it must be the current need to flow almost 4x larger than 0.9 VGS, right? So it doesn't follow the scale law model, and also the saturation. In saturation, the current should not change over VDS variation, but in reality, there's a little change in current in saturation for different VDS. So this is a different the effect that we can expect from the actual SPICE model. So what would be the reason for that? The first reason is the velocity saturation. So far we just assume that the velocity is just proportional to electrical field strength. The proportional rate is defined by the mobility for MOS and for electron and hole differently. So electrical field strength of the electrical field is VDS over L. L is channel length. That would be like that. So if you apply more volt, if you have a bigger VDS, then you get the higher E field and the faster the electron speed. But at high speed, this is not true. So if you increase electrical field, the actual velocity doesn't go up and up. You just saturate to a certain level. So there's just some saturation level there. It doesn't go all the way up. It just saturate. Because the carrier just scatter off the atoms. It just hit the atom and then it just hindered the movement of the electron is hindered by that the atom structures. So velocity reaches the V set eventually. It doesn't go above this. So for electron, it is about 6 to 10 times just 10 to the power of 6 centimeter per second. And for holes, little higher velocity. It's similar, but just about the same. So 4 to 8 times 10 to the power of 6. That would be the velocity saturation speed. So we can define the critical E field, saturation E field, that defines the speed of the electron. So if the speed is limited, what it means is that the current is actually limited. The actual current across the channel will be smaller. So for better model for velocity, electron velocity is mu E lateral electrical field versus 1 plus like this one. We have a critical the electrical field defined there. So you just follow like this curve, right? So in the conventional scale law device model, the IDS is defined by like this scale equation in saturation. So if you apply the VDS on VGS, VDD on VGS, then we know that the own current it increases with proportional to VDD scale. But if once the velocity saturated, the actual current equation defined like this, the actual velocity, maximum velocity, actually limit the current between drain and source. So in this case, even though we increase the supply voltage, then current doesn't grow with the scale law model. And so it just linearly, the current IDS linearly increases with the VDD. So in an actual transistor we are working on, and typically somewhere in between the square law model and linear model like this. So actually current is proportional to VDD power of to the power of alpha. So alpha is somewhere between 1 and 2. This is we can find the alpha empirically. So from the measurement, you can extrapolate or interpolate those numbers. So we can rewrite the transistor behavior equation using alpha power model in here. So for cutoff, VGS less than VTH is 0, and in linear device model, there's ID set, saturation current, that is defined by like this, but there's a scale, instead of a scale, we define alpha there. So that in saturation current times this factor VDS over VD set will give us a linear region current, and in saturation we define ID sets like this, right? And also VD set is also defined PV times some VGS minus VTH. In scale row device model, VD set was like a VGS minus VT, but it can be changed to some equation like that. So if you wanna know the exact VD set, you have to refer to the tool, and then the tool will report what would be the VD set and what would be the VTH. So you never hand calculate VD set and VTH, something like that. You have to look for such information whenever you have a you simulate the device or circuits. You have to look at the report from the simulator, SPICE simulation result. So this is the difference showing that the conventional scale law model, Shockley model is a scale law model versus alpha model. If you compare that, alpha law model is more similar to the actual simulation result, right? There's a channel length effect. So in the saturation, there's a because of the channel length modulation effect, we have a different current in saturation whenever if you change VDS in ideal scale law model. So IDS, VDS. For different VDS, the current doesn't change in ideal scale law model, but in reality, there's a slight change in current. This happened because channel length modulation. In near drain, there's a depletion region because this is a reverse biased diode. This reverse junction. There's a depletion region. If you increase the reverse voltage by increasing the drain voltage, you get the higher reverse junction voltage. This bulk is always tied to ground. So if you have a different VDS, this depletion region move back and forth depending on the drain voltage. If you have a higher drain voltage, then you get the larger depletion region. So effective channel length will be shorter, so meaning more current will flow. So in this depletion region, it's like a empty. There's no mobile carrier, but lots of a mobile carrier is under the channel. So, but even though in this depletion region there is no mobile carrier, there is a very strong electrical field. Any electron near this depletion region will swept by that strong electrical field. it is like a vacuum machine. Your vacuum machine, if you're collecting the dust, the vacuum air will suck up all the dust, right? The electron looks like a dust. There's a strong electrical field near the drain that will absorb all the electron in the channel. That's why we have like a triangular shape, the electrical profile there, because of the strong electrical field inside the depletion region. So actual width of depletion region grow with the reverse bias, meaning the higher VDS will make the reverse bias larger. So in that case, the effective channel length is shorter and more current will flow. So shorter effective channel length gives you more current, so IDS increase with the VDS variation, right? If you increase the VDS, then IDS is larger. So this happen in the saturation region. Considering this channel length modulation, we can change the device model. We can add that 1 plus lambda VDS. By introducing this lambda VDS, we can add some dependency on the VDS. The current will change for different VDS with some proportional factor there, lambda. This lambda is channel length modulation coefficient. So we can find that empirically to fit that IV characteristic with this model, right? So we can find the lambda to fit the actual device behavior. Another effect is the body effect. Body effect is that, for example, we learned that VTH, the threshold voltage as gate voltage to invert the channel. But for the body connection, if we have a different body voltage, then channel inversion happen at different voltage. So far we just assume that for VTH, if the body is connected to ground, we measure the VTH, VT to make the channel inversion. But if we have a different voltage at there, V body, the VTH will different. So actually VT increases if the source voltage, so if this is kind of relative voltage. So for digital design, we will have all the body will tie to ground. If the source voltage is changed, so relative voltage will be different between body and the source. So if we have a higher source voltage, then the source voltage increases, then threshold voltage increases. It looks like when the reason why, if you look at that, this compare this left and right figure, so source VS is less, for example, in this case, VDS is greater than 0 voltage, then source node is higher than 0 volt. If you compare that with the left, it looks like a body voltage is similar to minus less than ground, the equivalent to structure, right? So if the body on the left hand side, if the body voltage is less than ground, then the voltage we have to apply here to make the channel inversion, it must be greater, right? You have to invert the channel. The voltage required to invert it would be larger because of the negative body voltage. The same thing, same concept can be applied. If the source voltage is higher compared to the body voltage, then this also require more voltage to invert the channel, right? Right. So the VTH changes for the body potential. So those are kind of the relative voltage between source and body. So we know that the VT increases with VS. This is called the body effect. This is also same for VTH with the minus V body, right? The lower body voltage will increase the VT, right? This is called the body. So you can think of this body effect in two different scenarios. You have to understand that. We can model this body effect. So VTH is defined by the VT0. VT0 is the body voltage is zero, and there's just some gamma there. There's the surface potential voltage, and we have a VSB, right? So VSB, so plus minus VSB actually define the VTH. So if you have a higher VSB, larger than, if the VSB greater than 0, then VTH can go up. But if the VSB less than 0, then VT threshold voltage will go down, right? According to this equation. So surface potential voltage is defined by this device equation that depending on the doping level, Na, and Ni is intrinsic carrier concentration. So for example, if you have a higher doping on the channel for NMOS here, the body piece of. So if you more doping on the piece of the positive, the more hole onto this piece of layer, if you have a more doping in there, then would that increase the VT or decrease the VT? So you can think of that if you have a more hole in the P substrate, it will take more effort to make this channel inversion. We have to fill in the channel electron on the surface by applying the VGS, larger VGS. So meaning we need more VT, increase the VTH, more doping on this the channel will increase the VTH. We can see that effect in this equation. If you have more doping, right, on the channel surface, on the channel, definitely you put more doping on the P type right here for NMOS. So if you have more doping on the surface, that will increase the Vs, and that will increase the Vs, and that will go up. The VTH will go up, right? The gamma, the body effect coefficient, that can be also defined like that, and Na here. This gamma also increases, right? Here, that totally so Vs goes up and gamma goes up, so overall VT will go up with the doping. So typically there are different VTH provided by the process. So there's usually 3 different VTH model. There's model device, the regular VTH device, and low VTH device, and high VTH device. In sometimes ultra low VTH device there. So how we control this VTH for all different devices? We control the doping level on the surface. By controlling that, we can have a different VTH device. Now let's take a look at the off transistor behavior. What would happen in cutoff? In conventional model, the scale law model, we assume that when the VGS is less than VTH, then there's no current. But in reality, there's a little small amount of the current still flow. That doesn't go directly zero. So it can go, the current movement is linearly. This is kind of a log scale. So this linear scale, linear line means exponentially current goes down for less VGS. So this sub-threshold region, there's also current still flow, but exponentially decaying the current. We also need to understand what are the leakage sources. We have 4 leakage sources in this slide explained. First is sub-threshold conduction for VGS less than VTH, VT. There's still current flows between drain and source, right? This is one thing that so transistor doesn't turn off abruptly from on to off for less than VGS. VGS less than VT here. And also there's a junction leakage in we have a lot of reverse junction and diode inside the transistor structure. Even though there's a reverse biased, there's a non-zero current, right? From the current voltage equation VD current, even with the so plus minus out here, plus minus. If we increase voltage over diode, we will follow the exponential curve. But once the VD less than 0, then there's still current flows. There's the leakage current for reverse junction. So reverse bias PN junction still flows non-zero current there. And also there's a leakage, gate leakage there. If you have a turn on, so voltage applied there on the gate, the current still flow through this gate and channel. If you know that, if you look at the structure there, this gate and surface channel is the capacitive. They're supposed to be 0 DC current, but because of tunneling effect, there's a very slight amount of a current flows between gate and surface. This happened because we are dealing with a very thin gate dielectric there. So fine process will have always non-zero current flow through that gate to a channel. So one of those, so the biggest contributor for the leakage is the sub-threshold leakage, the biggest source in the modern transistor there. So even though you're applying the 0 there, there's also non-zero leakage current there between drain and source, right? Since there is a certain voltage applied there, it still flows. For example, if we have an inverter there, inverter gate is driven to 0, and then output will have a VDD at the output. Even though NMOS is turned off, there's a finite voltage across the drain and source for NMOS. There's a leakage current flow through the device still. There's also non-zero current there, so you have to double check. Try to minimize the leakage. In modern process, leakage current is non-negligible. So to reduce the leakage current, you have to use high VT device. So if the VTH is larger, then we get the less leakage current. So if you don't care about the speed or performance, you better use high VT device to reduce the leakage. Sub-threshold leakage model we can write there for VGS less than VT TH. I explained that this model follows the exponential curve. So here we have an overdrive voltage VGS minus VT proportional. This is the exponential function there. If you recall the diode model, VD versus ID diode model is ID equal to IS times exponential VD over NVT. If you want to model something like that. So this is a typical the diode model that we had learned. If you compare that with that, very similar, right? Except that VD is replaced by VGS minus VT, overdrive voltage. And also we have a VDS dependency in there. Here N is some process dependent variable that is typically similar to or approximately 1.4 to 1.5, like that. So in the sub-threshold region, the actual current grows exponentially to the overdrive voltage there. Dibble effect. Dibble is drain-induced barrier lowering. So actually, the drain voltage also affect the VTH. The threshold voltage it also depends on the VDS. So higher VD, so that lower the threshold voltage. So if you have a higher drain voltage, then the sub-threshold leakage will increase or decrease. You know that higher drain voltage reduce the VTH, meaning sub-threshold leakage will be increased because the threshold voltage lowered, then that will increase the leakage current. In the reverse junction, PN junction, we have the current equation that comes from the diode equation. This equation is more the detail. We have additional -1 factor there to model the reverse junction leakage here. This is minus IS, right? So in this case, we can model the reverse junction leakage current IS there. So IS depends on the doping level. So also the area and the perimeter of the diffusion region. So we have so many in typical transistor. We have so many reverse junction diode here, right? The left is NMOS, right is PMOS. All these leakage diode reverse junction leakage depends on the area, right? Doping level of those things. So typically the junction leakage is 1 femto to less than 1 femtoamp per micrometer square. The gate leakage happen, carrier may tunnel through the very thin gate oxide. So we can predict the tunneling current as you so oxide thickness is narrower and narrower, and also as we narrow down the oxide thickness, the supply voltage will go down, right? The device cannot handle such high voltage. So for finer process, this T oxide thickness goes down and supply goes down. As you can see, the gate leakage going up and up, right? So for finer process, gate leakage can be the big effect, and we have to take that into account, especially for mobile application like a cell phone. You want to have your machine or hand cell phone running longer. So the gate leakage was negligible for older process, but we will see some critical point where the gate leakage is large. But as currently the biggest leakage is the subthreshold leakage current or off current, like between drain and source. There's always non-zero leakage current there. We also have a temperature sensitivities. If we have an increased temperature, that will reduce the mobility, because we have a atom structure there. Electron moves around the atom, right? Here, if the temperature increased, then the atom will vibrate, more vibration, and the electron hard to pass through this structure. That will reduce the mobility and increase some resistance, or the mobility goes down, going down. So that effectively reduced, but even though the mobility is reduced, it reduced the VTH. So it can, because of the structure moving around, so slight amount of current can easily so the state is not stable. So even with the less less VGS applied, a small amount of current, more leakage current will flow for increasing temperature. So if you draw the curve, typical curve like this, so for low temperature to high temperature, moves like this. So this is the ID versus VGS. So this is the low temperature. This is high temp. So for higher temperature, the typical IDS, absolute IDS goes down, right, compared to the low temperature curve. But the VTH goes low, right? Even smaller VTH current flows. So ion decrease with the temperature, but I-off increase with the temperature, as shown in here. So increasing temperature lower the actual turn on current, but the low side current increases. So this is because the increasing temperature reduces the VT and reduces the mobility there. This is a very important fact that you have to remember. So what happens if the transistor is not ideal, but they still behave like a switch for our digital operation? But these effects it is important when you determine the supply voltage choice and also designing, you are using the logical effort, and also quiescent power consumption, and operation of the path transistor. Path transistor operation strongly depends on VTH, right? That directly increase the that affect the on resistance, and that will determine the speed. And also the reliability, because the MMOS cannot pass the VDD strongly, right? The output goes only VDD minus VTH, right? So there's just some degradation if you use only single transistor the logic there. And also you have to consider the temperature of the operation. For the desired temperature, you have to guarantee your function. So you have to always know that what kind of the temperature range you want to support for your design. Other than temperature, there's also parameter variation. So there are so many uncertainty in actual fabrication. The physical dimension like L and VTH, or physical property VTH and oxide thickness of all these transistors vary around the typical value. From the typical value to there is some different variation of the device characteristic because of all these variation. So your circuit must operate or reliably function for all these different corners. For different corner, what will happen is the MMOS, the typical is for MMOS and PMOS the typical speed, but if the fast corner goes to fast corner, then MMOS and PMOS both fast, meaning VTH lower. For slow corner, MMOS slow and PMOS slow. Typically happen when the VTH goes up. What happen if the MMOS is slow and PMOS is fast? Then, or what happened to MMOS is fast and PMOS is slow? All those 5 corners, we have 5 cases, right? 5 corners, that must be the guaranteed. The function must be checked under those 5 corner cases. For example, for fast corner, L effective channel length may be shorter and VTH lower, oxide thickness and thinner. So in these cases, that will correspond to fast corner. For slow corner is opposite, right? For low, short channel length and high VT and thicker T oxide. All those physical parameters will affect the speed and corners. So slow is opposite of those, right? So typically, all those parameters not all parameters not independent. Meaning, so one will affect. So thinner oxide will make a different. So thinner means the lower. So lower VT, because if you have a thinner oxide there, the more electrical field, even though you apply the same voltage there, the electrical field across those two gate and surface will be greater. So it will take less voltage to make the channel inversion. So that will effectively lead to lower VT. So thin oxide leads to low VT, something like that. So all those parameters closely related. So not all parameters are independent for NMOS and PMOS. So all these are closely related. Other than device variation, we also have an environmental variation. So we can change, the supply voltage may change, and also temperature may change in time and space. So for fast operation, device will work faster when VDD is larger, or temperature goes lower, then the device will faster, because those conditions will increase the current. ID, yes. So we can define the environmental variable for fast corner and typical and slow. So fast, for typical operation, supply voltage 1.8 and temperature is 70 degrees, for example. For fast corner, we can increase the supply voltage 10%. We can decrease the supply voltage 10%, and also temperature 125 C, and for fast corner 0 degrees C or minus 40 C. So these are something that you want to guarantee the operation. So typically minus 40 C to 125 C, we check the temperature operation. And also for voltage, we usually plus minus 10% variation is checked for reliable operation. Then we can guarantee that we guarantee the operation, and we can tape out and see the actual silicon works properly. So process of corners. So typically the process is like statistically, we have different samples. For example, we have a Gaussian distribution of this sample. Your typical, slow, fast. So statistically define the sample we will expect. We will get some worst case, extreme case of the device model is provided. So if the device works in all three or worst case corners, then you can guarantee that it will work for any variation. Between those variation you will cover the operation. So we define the process corner with the letter, the typical, fast, and slow. So we can NMOS speed and PMOS speed and supply voltage and temperature. All these 4 parameters can be described as typical, fast, and slow cases, right?